Hello, and welcome to the Altera training presentation, Implementing MIPI Solutions and Altera FPGAs. By the end of this training, you will be able to define and describe the Altera IP used in building MIPI solutions. You will also be able to configure these IP in the Quartus Prime Pro software for your specific implementation. We will start with an introduction to the MIPI specification. Then, we will introduce Altera's MIPI IP. Next, we will discuss the flow for building a MIPI solution using the IP. We will end this course with a look at the IP design example. So what is MIPI? MIPI stands for Mobile Industry Processor Interface Alliance. It's an association of nearly all manufacturers of applications or hardware in the mobile communication space, as well as the entertainment electronics industry. Its goal is to define and maintain the standards used for mobile products. Intel has been a member of the alliance since 2004. Within the MIPI standard are multiple specifications. This slide lists 3 of them, namely CSI2, DSI2, and DeFi. CSI2, which stands for Camera Serial Interface, is a high-speed protocol used for connecting a camera to a host processor. It defines the signaling needed for both data and control transmission between transmitter and receiver. DSI2, which stands for Display Serial Interface, is another high-speed protocol, but it is used for embedded displays in devices like smartphones, tablets, and smartwatches. Like CSI2, DSI2 defines the communication between transmitter and receiver for data and control. DeFi provides the high-speed physical layer used by upper-layer protocols like CSI2 and DSI2 for component-to-component communication. It defines source synchronous data transmissions supporting up to 8 lanes. Again, these are 3 of the many upper and physical layer specifications defined by MIPI. To be complete, here we can see several applications beyond mobile devices that use MIPI connections, including automotive, VR, healthcare, and industrial. In this next section, let's look at the MIPI IP from Altera. Altera currently offers the MIPI CSI2 IP and the MIPI DeFi IP. This block diagram shows the receive functional block diagram for a CSI2 camera to host interface. As you can see, it uses both MIPI IP. The first block on the left is the DeFi receive. Its input is a serial interface supporting up to 8 lanes. Out of the Phi and into the CSI2 receive IP is the Phi Protocol Interface, or PPI. As you can see on the right, the CSI2 IP is divided into 2 sub-blocks, the CSI2 Receive Protocol block and the CB2 AXI block. The first block implements the CSI2 Receive Protocol, while the second block handles clocked video to AXI conversion. A memory-mapped interface is provided for register access to the sub-blocks. Note the transmit block diagram would look similar, just in the opposite direction. In the table here, we can see some of the features of the CSI2 IP. The IP supports version 3.0 of the CSI spec. You can configure the IP for 1, 2, 4, or 8 DeFi lanes. The IP uses a 16-bit wide PPI per lane. The IP can be configured for 1, 2, or 4 pixels in parallel. The IP can operate in one of 2 modes, video or pass-through. We will cover these in an upcoming slide. For access to the IP's internal control and status registers, the IP provides an Avalon memory-mapped interface. For streaming video data, the IP uses AXI4 Stream. The IP supports raw data formats from RAW6 to RAW24, as shown in this table. It also supports RGB 444, 555, 565, 666, and 888. For YUV, it supports YUV 420 in 8-bit, 10-bit, and 8-bit legacy modes, as well as YUV 422 in 8-bit and 10-bit modes. Now, let's examine the modules, functions, and interfaces that make up the sub-blocks in the receive path of the CSI2 IP when configured in video mode. Inside the MIPI CSI2 Receive Protocol sub-block, we find the PPI low-level protocol module receives byte data and extracts the real video information. Multiple modules implement protocol layers for lane management, CRC, error detection, and byte-to-pixel conversion. Extracted and formatted video is then presented at its native clocked video interface. Inside the clocked video to AXI converter, CV to AXI, we find modules to convert clocked video data to AXI4 stream video data including a virtual channel splitter, a resolution detector, and a scheduler. AXE4 stream video packets are presented on the output. These packets follow the pattern of a single image information meta packet, followed by video packets, and then a single end-of-field meta packet. The diagram highlights how the virtual channels are converted into multiple parallel paths and AXE4 stream interfaces into the FPGA fabric. Again, the Avalon memory mapped interface provides access to internal control and status registers in both sub-blocks, mainly for the transfer of authentication messages. Though the slide shows only the receive IP, the transmit IP has similar but opposite blocks. The diagram also shows the IP clock domains, but we will cover this topic later in the course. The diagram shows how the CSI2 modules and paths change when pass-through mode is enabled. Pass-through mode allows you to implement custom processing of CSI2 packets. Processing the IP does not support directly. For the receive IP in pass-through mode, the entire received CSI2 packet is simply routed to the AXE4 streaming MIPI packet interface. Thus, you could route the entire unprocessed packet to another device, or you could separate video streams that have been combined in some way. For the transmit IP in pass-through mode, your FPGA logic must assemble a packet, or reuse a previously assembled packet, and pass it to the IP for transmission. The packet is passed through the IP unaltered. Using this mode, you can really support systems where streaming channels are combined in customized ways. In pass-through mode, the CSI2 received protocol sub-block is the same as in video mode up to the CRC, the depacketizer, and the error detection modules. Instead of the byte-to-pixel module, we find the auxiliary output block that directly passes the packet out of the AXE4 streaming MIPI packet interface, completely bypassing the CV2 AXE sub-block. You still have the Avalon memory mapped interface to provide access to internal CSRs in the protocol sub-block. And again, the slide shows only the receive IP. The transmit IP has similar but opposite blocks. This table lists some features of the MIPI DeFi IP. The IP supports version 2.5 of the DeFi spec. It supports 1, 2, 4, or 8 lanes and speeds of 3.5 gigabits per second per lane for Agilex D series and Agilex E series Group A. Lane speeds of 2.5 gigabits per second per lane are supported in Agilex E-Series Group B. All lane configurations require an additional lane for the clock. You can operate the IP in high-speed or low-power modes. The IP is unidirectional and must be configured in either receive or transmit mode. The IP uses the PHY protocol interface or PPI to connect to the CSI2 or DSI2 application, whether from Altera or another vendor. The IP has an AXE4 Lite interface for access to internal control and status registers. The IP supports a direct connection to a compliance component without using passive circuitry or external third-party components. Here is a block diagram of the DeFi IP configured for receive operation. Starting from the MIPI link on the right, each lane passes through a DeFi layer, which includes I/O buffers for high speed and low power, and a deserializer. Each lane then passes through a PCS layer and through the PPI for connection to the upper layer. In our next section, let's look at some details on how to build a MIPI solution in an Agilex 5 device. The Agilex 5 FPGA I/O are constructed using 4 separate I/O bank types. These are the high-speed or HS I/O bank, the high-voltage or HV I/O bank, the Secure Device Manager or SDM I/O bank, and the Hard Processor System, or HPS I/O bank. The banks are arranged around the periphery of the device as shown in the diagram or in a similar manner. Check your device user guide for your target device's exact I/O bank configuration. Note that the purpose of this diagram is not to display all periphery resources, as you will notice it does not show the transceivers. MIPI support is limited to the HS I/O banks, so we will quickly review the HS I/O architecture. Each HS I/O bank contains 2 subbanks, the top index subbank and the bottom index subbank as shown in the diagram. The top index subbank is on the left and contains pin indices 48 to 95. The bottom index subbank is on the right and contains pin indices 0 to 47. The pin indices indicate relative locations within the I/O bank. These pin indices map to the FPGA physical I/O pins. See the device user guide to learn the index to pin mapping for your target FPGA. Each I/O subbank contains 4 I/O lanes. These are shown as 4 vertical groupings in each subbank. Each I/O lane contains 12 I/O pins. These you can see within the lane groupings. These pins support both single-ended and differential operation. So putting this together, each subbank can host up to 48 single-ended or 24 true differential pins. While all HSIO banks support MIPI interfaces, a single I/O bank supports a maximum of 7 total MIPI interfaces. This is because the hardware reserves one of the byte blocks for on-chip termination calibration and the reference clock. The maximum number of MIPI interfaces is 3 when the IP is configured for 8 lane interfaces. MIPI interfaces must use dedicated locations in the I/O banks, as this table and the next indicate. Each I/O bank has 8 possible MIPI byte locations. Each byte location consists of specific pin locations for the interface's lanes, plus a separate lane for the clock. The table on this slide shows the byte locations for the 4 bytes in the bottom index subbank containing pin indices 0 to 47. For each index, you see the pins used for the by 1, by 2, by 4, and by 8 lane configurations. So, for example, a by 4 MIPI interface in byte location 0 would use pin indices 0-3 and 6 to 9, with indices 4 and 5 as the clock. Notice the clock is in the same location for all of the interfaces in that byte location except for the by 8. For the by 8, 2 byte locations share a single clock. So byte 1 uses the clock from byte 0, and byte 3 uses the clock from byte 2. For completeness, this table shows the same layout occurring for the top index subbank with byte locations 4 to 7. Now that we understand how MIPI is implemented physically in the FPGA, let's look at how to build a MIPI interface in Quartus. We start by launching the MIPI CSI2 IP parameter editor from the IP library in Quartus or Platform Designer. The parameter editor is divided into 5 sections, 4 of which you can modify. The first is the General Options section. Here you can select between receive and transmit, and you can choose the line buffer size. For a receive IP, this is in units of pixels. For a transmit IP, this is in bytes. There is also a tick box in the section allowing you to enable CSI2 scrambling in the transmit path or CSI2 descrambling in the receive path. In the DeFi interface options section, select the number of lanes to implement in the DeFi IP that you will connect to the CSI2 IP. This is necessary to properly configure the PPI bus between the 2 IP. It currently defaults to 16 bits per lane. For the number of lanes, select 1 clock and 1 data, 1 clock and 2 data, 1 clock and 4 data, or 1 clock and 8 data. In the video streaming interface options section, choose the number of AXI4 stream or CSI2 virtual channels that will share the IP from 1 to 4. Then select the number of pixels to stream in parallel, either 1, 2, or 4. See the IP user guide for more details on CSI2 virtual channel support. This table lists the video data types available in the video unpacking options section of the parameter editor. To limit the FPGA resources used by the IP, choose only the video types that you need. Note that the YUV video data type is supported in the receive-only IP configuration. With our IP now generated, let's look at the IP interfaces that you need to connect. On the left, you can see the IP interfaces in the receive, and on the right, you see the corresponding IP interfaces on the transmit. First is the PPI for connecting to the required DeFi IP. Next are the AXI4 stream interfaces that connect to the video capturing or generating logic in the FPGA fabric. Both IP also have AXI4 stream pass-through interfaces, if enabled. Note that if you enabled multiple virtual channels in the IP, you will get 1 transmit pass-through interface per channel. These channels pass through a mux for transmission, so if one channel is currently transmitting, the other channels will be back-pressured. For IP clocks, you have the AXI4 stream clock, which drives the IP core logic, and the Avalon interface CSRs. Then each IP implementation has 2 high-speed word clocks for connecting the PPI to the DeFi IP. The diagram here again shows the receive IP, but the transmit IP would be similar. For resets, each CSI2 IP clock domain has an associated reset. The DeFi IP configures the Agilex 5 I/O banks to implement the MIPI physical layer, so while you could use a CSI2 or DSI2 IP from another vendor, the DeFi IP is required. Like with the CSI2 IP, use the parameter editor from the IP catalog to set up the core. The screen captures on this slide shows some of the options available. On the DeFi IP tab, on the IP configuration sub-tab, you select to use one PLL for all links, or enable two PLLs that can be shared by the different links. Here you set the RZQ pin location, define the lengths of the transmit initial skew calibration pattern, and the transmit alternate skew calibration pattern. These patterns run automatically during initialization, but are also under register control. Please see the IP user guide for more details on the IP's initialization and calibration processes. On the PLL sub-tab, shown in the center screen capture, you define your IP PLL settings including the reference clock pin configuration. On the example design sub-tab, you choose options for the example design generated by the IP tool. We will learn more about the example design in upcoming slides. After the DeFi IP tab, you see 7 link tabs for link 0 to link 6. Use these tabs to configure each of the DeFi interfaces that will be used in a single I/O bank. Remember, we learned that each DeFi link is either receive or transmit, and that a maximum of 7 MIPI interfaces are supported in one I/O bank. So for each link here, you select options like receive or transmit operation, which PLL is used as its source if there are multiple, the link bit rate, the number of clock and data lanes, the byte location within the I/O bank, enabling or disabling calibration, receive or transmit interface timing parameters. These parameters can be auto-populated or set manually. See the IP user guide for more details on the timing parameters, both auto and manual. After generating your DeFi IP, here are its interfaces to which you connect. There are the DeFi connections to the external link. These, of course, get mapped to FPGA I/O pins. Remember, Agilex 5 FPGAs do not require intermediate circuitry or components to connect to the other end of the link. The RZQ interface for on-chip termination, or OCT, calibration, and the reference clock for the PLLs are also mapped to pins for external connection. Internally, you connect the PPI interfaces to the CSI2 or DSI2 IP in the FPGA fabric. You must make sure to connect the upper layer IP as you specified in the DeFi parameter editor link settings. Connect the AXE4 Lite interface to your control logic to access the IP's CSRs. The IP also provides a core register bus interface, which extends the AXE4 Lite interface to other IPs within the FPGA. This allows a single AXE4 Lite interface to access CSRs within multiple IP cores. The example design uses the core register bus to extend the CSR space to the traffic generator block. The DeFi IP gets configured to generate the clocks on the PPI to synchronize the transfers with the IP at the other end, like the CSI2 IP. These clocks are the transmit and receive high-speed word clocks. Their frequency will be set to the line rate divided by 16, the width of the PPI data bus. As we learned in the CSI2 IP section, these clocks are used only for the transmission of data between the IP. The CSI2 IP core runs off of the AXE4 stream clock. The frequency of the AXE4 stream clock must be the same or greater than the peak burst data rate on the external MIPI DeFi interface to prevent data loss due to insufficient throughput. Use the equation on this slide to determine a proper clock frequency. Altera recommends adding 10% to the frequency as a buffer. The table on this slide provides example numbers for some video types and line rates. For on-chip termination calibration, Altera recommends a 240 ohm resistor. The resistor should be connected to the RZQ pin at pin index 38 in byte location 3 or at pin index 62 in byte location 5. Once chosen, that byte location can no longer be used for the MIPI DeFi IP. You must select which location you intend to use when configuring the DeFi IP to ensure Quartus enforces the placement rules. In the parameter editor, RZQ0 maps to pin index 38 and RZQ1 maps to pin index 62. For DeFi PLL reference clocks, you must assign the MIPI reference clock to a dedicated clock pin on the FPGA. If your reference clock uses the true differential I/O standard, then that byte location chosen can no longer be used for the MIPI DeFi functions. So, in this case, it is recommended to place the reference clock in the same byte location as the RZQ pin. If your reference clock uses the LVC-MOS I/O standard, then that byte location is still available for MIPI DeFi use. There are additional pin placement restrictions when using the DeFi IP. When a particular byte location and number of lanes are chosen, then select pin indices cannot be used as single-ended pins. This table summarizes these restrictions for all 8-byte locations within an I/O block. So for example, if you implement a 4-lane interface in byte location 1, then pin indices 5, 10, 23, and 26 cannot be used as single-ended pins. The MIPI DeFi user guide contains additional design guidelines and recommendations. It includes information on how to share I/O banks with the MIPI IP, recommendations on board layout, and planning a reset strategy. For our last section, we will take a look at the MIPI design examples. There are 2 possible design examples to generate for the CSI2 IP, a design using receive and transmit subsystems, and a design with a receive subsystem only. Note simulation is not supported for the receive-only design example in Quartus version 24.1. An additional design example is available for the DeFi IP. The CSI2 design example demonstrates 2 MIPI interfaces with both CSI2 and DeFi IP. For the receive path, you have a CSI2 receive subsystem connected to a DeFi receive IP. For the transmit path, you have a CSI2 transmit subsystem connected to a DeFi TX IP. This is a fully functioning hardware design, so it includes the reset release IP required on all Agilex 5 devices, along with reset controllers and clock bridging. The design example is generated in Platform Designer, so you can open it to review or use it as a starting point for your own MIPI interface. You may also generate a simulation model of this design to study and better understand the IP's behavior in your favorite simulator. For simulation, a test bench is created to generate and validate image packets sent and received on the IP's AXI 4-stream video interfaces. The test bench matches the packet types to the types enabled in your IP configuration. Pass-through mode may also be simulated. Please review the MIPI CSI2 user guide for more details on the design example. The DeFi design example shows only the DeFi IP functioning in a system. A pattern generator is connected to the PPI of DeFi transmit IP, and a corresponding pattern checker is connected to the PPI of the DeFi receive IP. As a fully functioning hardware example, it also contains the reset release IP as well as a JTAG bridge to provide system console access to the IP's CSR registers. Use this design example if you plan to implement your own upper layer IP, so you may want only a functioning, pre-configured physical layer. With all MIPI IP, generate the design example from the Design Example tab in the Parameter Editor. The screen capture on this slide shows the CSI2 parameter editor. Select whether you want the synthesizable or simulatable model, or both, and then choose the HDL language for the model, Verilog or VHDL. Click on the Generate Example Design button at the top of the window and specify the target directory. See the user guide for the IP you're using to see instructions on how to launch the simulation with different supported simulation tools. This concludes our look at implementing MIPI solutions in Altera FPGAs. In the training, we learned that Altera offers MIPI solutions in the form of the DeFi and the CSI2 IP. The DeFi IP can be used standalone, but the CSI2 IP must be connected to the DeFi IP. We also saw that success in using the MIPI IP requires understanding Agilex 5 I/O layout and how the MIPI lanes must be placed. We saw how to do this in the IP parameter editor. Finally, we learned that generating fully functional hardware design examples is a great way to begin designing with the MIPI IP. Generate the design examples directly from the IP parameter editors. As cited in this training, locate all of this information and more in the MIPI IP user guides linked on this slide. If you have questions on MIPI in general, follow the link to the Alliance's main webpage. The Altera training team is always looking to improve our material. To do this, a survey will be emailed to your registration email address. We welcome any feedback you may have. Thank you again for viewing this training. Have a good day.